Good evening, everyone. I am Jyoti Kumari, research scholar from the Department of Physical Science, Banasthali, Vidyapith, Rajasthan. I am doing my research work under the supervision of Dr. Banwari Lal Chaudhary. I am here for presenting my work for International Conference on Energy Materials and Devices, which is organized by the Department of Physics, Banaras Hindu University, Varanasi. And the topic of my research is investigation for structural, electronic, and optical characterization of lithium-based chalcopyrite semiconductors by using the density functional theory. And my abstract number is C8. These are the contents which I am going to discuss in this presentation. First of all, we are talking about the inspiration. If we are talking about the current scenario, the population of the universe is inversely proportional to the production of energy in the form of electricity, and the organic fossil fuels are degrading day by day. So the demand of electricity is increasing rapidly, but the generation of the energy without polluting environment is a great challenge for all of us. In this relevance, the researchers and scientists are trying to make a device which is called photovoltaic device, which can convert the photon energy into the electrical energy. In this device, the main layer is the absorbing layer, which absorbs the photons and converts it into the electronic, into the electricity. So, in this, the chief abundant source of renewable energy is the solar energy, and the researchers are concentrated on finding a substitute materials which can be used to operate the solar energy as electricity. And we are also trying to find a substitute material for the absorbing layer. In this relevance, there are many materials are discovered, likewise perovskites, antiperovskites, double perovskites, half Uslers, and the chalcopyrite is one of them. The chalcopyrites having good applications for the photovoltaic device, the power conversion efficiency crosses from 22.8% nowadays, and they are very stable compounds at high pressure and high temperature. Introduction. These compounds having general formula I first, third, sixth. Here the first, third and sixth represents the first group, third group and sixth group elements. These compounds can be made by the combination of second group, fourth group and fifth group elements also. But here we have choose the first, third and sixth group elements. These group elements possess the body's center tetragonal symmetry, and they are belonging to the I-42 space group, and the space group number is 122. The chalcopyrite solar cells have great potential in efforts for the solar cell harvesting. If we are comparing the chalcopyrite solar cell to the silicon solar cell, the chalcopyrite solar cells are very low in cost, and the fabrication cost is also very low, and they are having the high charge carrier mobility. They are reliable and non-toxic and eco-friendly. The lifetime of these compounds are long-lasting and stable compounds. The silicon solar cells has been replaced by the chalcopyrite solar cells. In this work, the density functional theory is used. The density functional theory is based on the Hornberg-Kohn equation. That this theory is applicable on atoms, molecules, solids, and nuclei. It, provide, it provides the ground state property of a system. Likewise, ground state energy, and the volume at equilibrium, bulk modulus of elasticity, and the first derivative of the bulk modulus, etc. The density functional theory predicts a great variety of crystal properties. Likewise, the information about the structure, called the structure property, likewise lattice parameters, bond length, bond angle, atomic positions of a crystal in a unit cell, the electronic properties, likewise the charge density, electron density, density of states, band structure, and the band gap of a material, and total energy at the ground state, optical parameters, likewise optical conductivity, dielectric constants, reflectivity, reflection, etc. And the elastic properties likewise modulus of elasticity, thermoelectric and the thermodynamic properties as well. The simulation code have been used the Win2K code. The Win2K is a full potential all electron code which is developed by the Peter Blaha at the Institute for Material Chemistry, Technical University at Wien, Austria. It is based on the Kohn-Sham equation of density functional theory by using the full potential linearized augmented plane wave. Now we are discussing about the results. I have taken three materials called the chalcopyrite materials, namely lithium, aluminium, tellurium, lithium, gallium, tellurium, lithium, indium, tellurium. Here these are the structure of the three compounds, and I have firstly optimized these compounds by using the Morgan equation, which is by default implemented in the Win2K simulation code, and these are the calculated lattice parameters which are very closely agreed to the experimentally extracted lattice parameters, and this comparison of calculated and experimental extracted data confirms the accuracy of the calculation of structural properties. This is the Morgan equation which is used to optimize the crystal structure. Here, E naught stands for the equilibrium energy at the 0 Kelvin temperature, and B stands for the bulk modulus, and V dash stands for the first derivative of the bulk modulus, and V stands for the volume of the unit cell, and V naught stands for the equilibrium at 0 positions. And these parameters are calculated by optimizing the structure using Morgan equation. These are the calculated band structure. If we are going to make a device, then it is a necessary condition that the chosen material should be semiconductor. So if we want to know the material is insulator, conductor, or semiconductor. To decide this, we have to study the band structure of the compounds. So these are the calculated band structures of the three compounds. So here we can see that these the top of the valence band and the conduction of the bottom of the conduction band lies on the same gamma point. It means these are for all these three compounds. It means these three compounds poses direct band gap. So these compounds can be called the direct band gap semiconductors. And these are the calculated band gap by using the LDA, WC, PBE and PB-SOL exchange correlation potential, which is implemented in the simulation package. And uh, this is the calculated band gap as compared with the experimental band gap, and this comparison confirms our accuracy of band gap. So from the study of this band structure and band gap, we can say that these compounds are direct and narrow band gap semiconductor compounds, which is the beneficial for the for the use in the photovoltaic device. Now we have studied the optical optical properties. Likewise, I have calculated the real and imaginary part of the dielectric constant. From the real part of the dielectric constant epsilon 1, we conclude that all these three compounds show the anisotropic nature, and from the imaginary part of the dielectric constant, we can conclude the absorption takes place in the ultraviolet region, and small part is also in the visible region. And the optical band gap confirms the accuracy of the electronic band gap. And these are the absorption coefficient and optical conductivity, which is calculated also by the Windtuch simulation code. And from the absorption coefficient graph, we can conclude that the absorption takes place in the ultraviolet region, and small absorption takes place in the visible region also, so which is beneficial for the use in the photovoltaic device. And the optical conductivity takes place in the ultraviolet region of the electromagnetic spectrum. The optical properties are very important to study, because if we want a optoelectronic device, it is very important to see the response of the materials or compounds in the electromagnetic spectrum. So from this study, our conclusion is this: there are many advantages of the chalcopyrite structure solid. Likewise, from the optical graphs, we can say that they possess high optical absorption coefficient, and from the study of the band structure and band gap, we can say that they possess the direct and the narrow band gap. So they are the direct semiconductor compounds, and these compounds attract extensive attention of the researchers because of its non-toxicity. And these compounds with small semiconductor band gap can be useful for the thermoelectric generators. The thermoelectric generators convert the waste heat energy into the electrical energy, and for the electricity production as an alternative energy sources. So the chalcopyrite compounds can be the potential regarded as a promising absorber and a green alternative for the photovoltaic applications. Chalcopyrite has the advantage of low price, abundant reserve, and non-toxic. Thank you so much.